Greetings again. This is the second week of classes on video, and I'm going to talk about two things, computer models and classification of computers, and performance metrics, which we use to measure the performance of computers. So computers have evolved over time as other physical systems have. And the earliest, I guess, computer, in maybe a complete sense of the word computer, would be ENIAC architecture, which was completed in the late 40s. And ever since that time, people kept building these serial machines, which are also known as von Neumann architectures. They just preserved their essential form through 1970s, and then they were replaced by more advanced von Neumann architectures. They were still von Neumann architectures that had the capability to execute instructions in an overlap and pipeline fashion. And so these designs dominated the last quarter of the last century. And of course, then we began to have some more recent architectures, which are typically called superscalar architectures in multi-core engines. These are like 2000 plus, from 2000 on to today. Now, we talked about a slightly more abstract classification, and we called it Flynn's classification. This classification came fairly early in the game. It was actually announced by Flynn in the 60s. So he had the vision to see that these architectures that are now in use could really be realized. In the 60s, he could see this. And so his classification basically comes with 4 different classes of architectures. Single instruction, single data machines. We also abbreviate that as SISD. And it's really what's called a von Neumann architecture, a serial computer at best. And multiple instruction single data machines, the MISD machines, and I would like to think of them as pipeline computers, even though other interpretations can be given to this particular architecture or machine classification. And then the single instruction multiple data machines, which are the SIMD machines, and they are somewhat synonymous with array and vector processors. And then the most general form would be multiple instruction, multiple data machines, the MIMD architectures. So multiprocessors and distributed processors would be examples of this class of machines. So let's just take a look very quickly in some graphical form how these machines really operate. So as I say over here, the CPU executes one instruction at a time. This is our CPU here. And it is extracting programs, an instruction at a time from the memory that it interfaces with. And it then computes based on the operands it receives most of the time from memory, but sometimes within its own cache or scratch pad, which are not revealed in here. And then the results that get generated typically are returned to memory. And of course, there's an input and an output device for us to be able to enter and then also view our results, enter our operands or our files, our data, whatever it is that we want to compute on. And so that's the von Neumann architecture right there. And it is a classic SISD architecture or SISD machine. And it is actually somewhat enhanced, as it is stated here, by overlapping the execution of instructions. And that helps hide some of the time that the CPU may idle over waiting for results to come from memory. So, or operands, that is, and then returns to go back to memory. And so that overlap execution is something that hides it. Now, MISD architecture or machine classification is somewhat um, less populated, but one example that comes to mind, whether this completely fits the model, is also questionable, but at least we can think about it. And so our CPU is now stretched into maybe several instructions. Of course, these instructions will be handled at different stations, different segments of the CPU, and so the pipelining will give us what we call instruction level parallelism, because these instructions ultimately will be at different segments in different segments of our CPU, and will then execute concurrently or in parallel. So the rest of the architecture remains the same. You got to have an input medium and an output medium, and memory also. And again, we just have to show that this is not just the data, but operands and results are what we're really referring to here. And so this takes care of this architecture right there. And so other examples, as I said, can be constructed to account for MISD where the same data get subjected to multiple instructions. This may or may not be true in this example, because when we push different when we push our instructions through the segments of this pipe, the CPU pipeline here, we may or may not have the same data. But if we stretch our definition, I guess, in some way, and then consider a collection of operands as part of our program, so you can think of this as in fact constituting an example of MISD architecture. SIMD array is a little easier to grasp. So you see that in all these examples so far, we retained most of everything here, which is basically the IP, the input, output, the memory, and then the CPU. Now the CPU then actually is the control unit here, which instructs by way of instructions computations on this ALU array. So this is an array of ALUs, not one ALU, but a multitude of ALUs, not necessarily connected in the form of a grid I show you here, but it is some topology that actually provides the CPU with the ability to instruct these ALUs to do certain computations all at once. And so instead of like having for I want to some number do, you will have parallel for, and that parallel for will simply instruct a collection of these ALUs to perform addition, subtractions, whatever it is that you want to do. And of course, if you don't want to have all of these units here, like at the intersection of each of these points here in this array, let's say that you have a processor, you may want to disable, mask out some of the processors for prevent them from participating in a computation, and typically array processors come with that capability, so that you actually are able to involve only a subset of these processing elements. And I could technically mark some of these things so that you will understand what I am talking about here. Let's see if I can just pick a circular object here. So, you have these objects here, like so, and these objects, which are basically your processor or your ALUs, are the ones. If this were to be a grid, it doesn't have to be, but you could enable some subset of these. It won't be this random, but you could just enable a row of them or a column of them, or all the diagonal elements, or all of them at once. You could do those things to essentially compute a vector operation. Like I was saying, you could just do something like this for I, or would you say parallel for I equals, let's say, 1 to I less than some number, maybe 10, I plus plus. Let's see, right there. And just say you AI equals, BI plus CI. What this does, it makes this computation happen all at once. That is to say, all 10 additions here happen simultaneously by providing an instruction to 10, let's say, ALUs here, all of whom would ultimately compute the same addition. Now, of course, the CPU needs to work on data that would have to be preloaded or sometimes loaded from memory into the array. So for that, I show you a direct path here, and that direct path basically indicates how these processing elements will then be ordained with their operands before, in fact, this thing begins. Okay. So you get the gist of this machine classification, and then the last one is the most general machine type we can have, and we call this a multifunction and a multiprocessor architecture. And so again, the same structure remains: input, output, memory, but then what we have here is just this multiprocessor system, which takes care of all the computations. Now, what is not made obvious here in this diagram is how this engine really interacts with memory. So because it's got a whole bunch of processors, each of which would be interested in whatever we have in this memory, we need to think of this memory as some sort of a multi-port memory. It cannot be just one memory where lots of processors are trying to grab operands or return results into. It has to be that you have some bandwidth. And that bandwidth is typically provided by what we call an interconnection network. So think of these processing elements as being housed in this orange space here, and the memory itself is partitioned into, let's say, n modules, and now you have a system where the processors are able to communicate with the memory elements, and that communication is provided by what we call an interconnection network in between. And so, like I said, this really works like an n-port shared memory, where the memories can be considered to be contiguous, but then you have the number of ports to sustain this, or you can think of them as separate modules of memory. But interconnection network sort of makes it possible for these processing elements to actually access these memory elements. We're going to say a lot more about interconnection networks later, so I'm going to leave it at this. But the main idea is that this is really better suited to SIMD computations, where synchronization is better achieved. That is to say that these processing elements work in a lockstep fashion. And these processing elements are really elementary in this context. They are mostly ALUs, as I talked about. So it's even an exaggeration to call them PEs. They are mostly ALUs in the context of SIMD. So let me just say this so that you don't forget that. So PEs are ALUs. In the case of SIMD. Okay, so this is what I was saying, and so that's how it goes. Now the second version of this would be something like this. We also talked about this in class, and here we placed the interconnection network to allow these processing elements to communicate with one another, and then have their own memory elements where they could actually do the individual computation. So the more decentralized our system is, the better the model is suited to it, because we're basically saying that these processing elements will communicate once in a while, not that often, with one another through this network, but then most of the time they will engage their own computation. So that way we try to protect their try to isolate them if in fact they want to be isolated, and work on their own systems, the programs, computations. Um, so this would be better suited to decentralized or multiprocessing systems. Multi-cores could be viewed as perhaps similar architectures here, because multi-cores will have, each core will have its own memory and its own obviously capability to do computations with an ALU, but also the individual control. And the network will provide the connections between them. All right, so this is really the classification topic we covered in class, and now I'm going to switch to performance. So we began by talking about work and time, and we entered the subject of performance metrics. And then we agreed that work measures how much a system produces in a given time, and time measures how fast a system completes a given task. So these two concepts are fundamental to performance. Excuse me, because we want to get either work done in a given amount of time, a certain amount of work done in a given amount of time, and we don't settle for anything less. That's like how we want it, or we want to do something fast. We have a task, and we want to do it as fast as possible. So we can then derive from these two notions what we call the axioms of performance. If two systems A and B produce WA and WB work in time t, that is in the same amount of time, then system A is better than system B. It only makes sense to say that if and only if the work that A produces is greater than the work B produces. I mean, it's very trivial. It's just difficult not to, assume that this will be the sort of notion that would give us a metric that would compare two systems for work. Now, if two systems, A and B, complete W work in time TA and TB, respectively, then we say system A is better than system B if and only if TA is less than TB. Okay, so this time we're talking about A and B, being compared in time terms, and now we have to say that the time that A takes to compute something, the same thing, that is the W work, is less than TB for it to be better than better than B, I'm sorry. So, like I said, these two axioms express our desire to get more work done in a given amount of time, and to use less time for a given amount of work. If we don't fix one of these two metrics, then it is not really too meaningful to compare them using the other metric if we consider both metrics to be part of our measurement. Okay. Now, we could actually generalize this notion of work and time as metrics and part of our axioms. So for that, what we need to do is to basically consider two types of load, or two compare those in time or work terms, but then we actually pick two types of work. So if system A produces WA1 work of type 1 and WA2 work of type 2, so these are two different types of work, and system A produces WA1 and WA2 in those two categories of work, and it takes TA time to do this. Let me see if I can fix this real quick. Now, so it's the time that it takes, that is TA. And system B produces WB1 work of type 1 and WB2 work of type 2 in time TB. Now that's what we assume. Then we say that system A is better than system B if and only if WA1 plus WA2 is greater than TA over TB times WB1 plus WB2. So this obviously is something that comes out of what we call average performance. What we do here is we take WA1, add it to WA2, and then divide it by TA to assess how much work we get out of system A in time TA. And then we compare that with the work, total work that B does, normalized to the time it does it in, which is TB. So really this formula is very much, it is derived from this expression. Let's see if I can actually copy this somehow. If I just do this, if it copies, it's basically divided by TA is what this is, greater than, oops, this expression. Is that stuck in there? Divided by TB. Now, probably need to put parentheses around here. Okay, so effectively this is what this is, and that is obviously meaningful. We take the amount of work that A produces, total work that is, which is this, divided by time A, and then do the same thing with this, and divided by TB, and we say that system A is better than system B if in fact this inequality is held. Now keep in mind that we may still not really be measuring something that we desire if we still emphasize the total work that the two systems produce. If we don't care about time, then total work will be for A, the sum of WA1 and WA2, and the total work for system B, produced by system B, would be the sum of WB1 plus WB2. Now, if we don't care about the amount of time, then clearly one of these two systems would be better, depending upon which of the two amounts of work we just tallied is greater. So if this is greater, if this quantity here is greater than this, A will be better. If this quantity is greater than this, B will be better. All we're doing here is we're comparing the ratio, not these two numbers by themselves. And clearly these numbers would come out not necessarily in agreement with work comparisons, because we might really have these time values arranged in such a way that we may have this inequality hold, but we may also have WB1 plus WB2 to be greater than WA1 plus WA2. In other words, we may still prefer system B over system A if we just paid attention to only the work amount. In the same way the time applies here. It's a little more, I guess, direct when we compare work, because we're not necessarily looking at the time as individual pieces, but just like a total time. So effectively what I'm saying is this measure makes sense only if we really are interested in the ratio of total work to total time comparison, not work comparison. Now in the second part, what we're doing, we're actually comparing time. So we say that if system A completes WA work of type 1 and type 2 in time TA1 and TA2, and system B completes WB work of type 1 and type 2 in time TB1 and TB2, this time we actually take system A preferred over to B if and only if TA1 plus TA2 is greater than WA divided by WB times TB1 plus TB2. Here again, what we're doing here is we're taking the total time. I think my inequality has just gone the other direction. Let me just actually quickly change it. I just realized it has to be this way. So what we're doing is we're actually computing service time by taking this sum, dividing it by WA, move this down here. So you have total time over total work. That is service time here in some average sense. And that we compare to total time taken by system B divided by work. And now we're just comparing this time the service times in an average sense. And again, if we don't really care how much work gets done, but only in the amount of time that we get it done, this will not factor into the argument. We might as well assume that they are the same, and all we do is we just look at the total time used by system A versus total time used by system B, and we say A is better than B if and only if the total time that A consumes to get this work done versus total time that B consumes to get its work done. Of course, if they are the same, that makes, it is consistent with our notion of time priority. If they're different, then this ratio will obviously impact the conclusion, because depending upon whether this is greater or less than 1, we may actually alter the inequality between these two total time values. So again, you could see what's happening here is that when we want to bring time and work together, we really have to understand what we're trying to measure, whether it's average work over time or it's average time over work. What we're trying here is to relate the two performance metrics together. In the earlier cases, what we were doing was taking work separately and taking time separately and putting the priorities on those for the same amount of work or for the same amount of time. Now, so throughput, implicitly debated or discussed in this earlier discussion we had just now, is really another key metric of performance, as we just noticed, and it just measures work averaged over time. The higher the throughput, the better the performance in average sense. We can say this only in an average sense. Now, I've written this formula at the end of the class and ask you to derive this, but effectively this is the harmonic mean of a set of throughputs, which are like x1 through xm. This is a weighted harmonic mean where the weights are W1, W2, Wm, and they add up to W. So the ratios here collectively added together, they're all fractions and they will add up to 1. Bring them under the common denominator, so you'll have W1 plus W2 plus Wm over W, which is equal to 1. So this is called the harmonic mean. Now, whenever we actually compare things in an average sense, and it's a rate like this would be, throughput is basically work over time, we use harmonic mean. And you can actually show that here the total work over total time is what this harmonic mean refers to. That is to say, if you do the algebra, if you replace these x sub i's, which I think I've never written down here, let me just make that clear. If I don't write that, you may actually not be able to get this. Let me just write it right there. So the x sub i's would be equal to wi over ti, and this is true for m. Okay, so now given that, I think you can derive, you can actually show that the average throughput as it is expressed here is the same as W over T, where T is, let me just also emphasize that, where T is this thing here. T1 plus T2 T M. Okay. All right, so this is how it's supposed to be. And now that you know what T is, what x sub I is, x sub i's are, you could actually show that the total work over total time is what the throughput expresses. So this, I guess, is what we covered during the second week, and in the third week, we talked more about work and time. We talked about work and service time functions, discussed ratio games, and talked about the CPI measure and the power performance metrics, which we will do in the next video. Until then, take care.